Hey everyone, I'm going to give you some quick examples of zero knowledge proofs. Now, this is always one of those fascinating topics for me where somebody will come up with an idea, and because these proofs demand creative solutions, they'll say something and I'll go, you know what? I have no idea. Because there are so many options and it's really hard to prove something wrong. But we'll see that as we go on. So, zero knowledge proofs, the basic idea of them is that we want to basically um, demonstrate to somebody with a high degree of confidence that we know a solution to something without revealing that solution. So it's like saying, I've solved a crossword puzzle. How can you give something to someone for them to verify without actually showing them the crossword puzzle? These very interesting problems. And the crux of it, a lot of it is if you can divide the problem, the solution into two parts, um, and that if you get those two parts and put them together, they'll give you the full solution. But if you can split it into two parts and offer them only one half of it at a time, and you repeat that so that you know that thing that you're showing them is not the same each time, it's a different part of it, but the two together would give you a solution. If you can give them the option of one or the other, um, if you do that enough times, it's really hard to fake, knowing which side they're going to pick each time. Um, and if you do that enough times, if you do it, 1,000 times, it's going to be very hard for them to believe that you were able to fake both of these halves both times when they get to pick which side. So I'll explain that in a second, and it'll probably make more sense when I go through a demo. So the classic example of a zero knowledge proof is this one here. We've got a wonderful person in the pigtails who says, I know how to walk through walls. And you go, that's crazy. How do you know how to walk through walls? This is you going, that's crazy. So the person in the pink says, I know, I'll come up with a solution, how I can demonstrate this to you. I'm going to go, you go hide around the corner, and I'm going to walk down one of these sides of the cave. I can walk down side A or side B. And then, let me move my face down here. Then I'll call you to come back, and you get to yell out one of two things. You can yell out A or B. And whichever side you yell out, I'm going to come walking around. So that's the premise of it. And let me get rid of that. So he goes, yes, I agree. And they go to do that. So let's say that this person here walks down side A. She's sitting here, and then the green person comes back again, and he yells outside, A. She goes, oh, no worries, that's easy. And she just walks back out here and goes, hello, here I am. That's really easy for her to do. However, if he comes back and she's down side A, and he yells outside B, well, what she has to do is she has to walk through the cave, through that wall, and then walk out on side B and go, hello, how are you? So that's how a person who can walk through walls would demonstrate that they can walk through walls. Now, the real crux of a zero knowledge proof is you actually have to repeat that a whole bunch of times because you could have a faker. Now, this is always a really cool way to judge if a zero knowledge proof leaks any information, is you get a fake person. So instead of this being this person in the purple here, let's say it's me, and I assure you I cannot walk through walls. So if I was trying to fool this lovely green person over here, I might stand in here. This is what I look like. Rah, very scary. And I might say, here's the solution. I can walk through walls. Trust me, trust me. And then I might go hide down side A, right? I'll sit down here. When the green person comes back, I'm really, really hoping that he says side A. Because if he says side A, I can walk out and go, ta-da, here I am. I can walk through walls, even though I can't. So what he'll do is he'll go, oh, that's really impressive, but it's 50-50 chance. I don't really believe you. Let's do it again. And I go, okay, yes, no, that's fair. Let's do it again. And this time, I might walk down side B, and I'll be sitting here waiting for him to come back, and I'm sure as hell hoping he'll yell out side B. And he comes back, and let's say he yells out side B. And I go, yes, oh, my luck's come up again. You can see first time it was 50-50 odds that I'd guess the right side. And the next time it's another 50-50 odds, so it's 1 in 4 chance that he'd pick the side that I was on both times. But if we did that 10 times, if we did that 1,000 times, it's going to be really hard for me to always pick the right side that he's going to guess. So that's the nature of a zero knowledge proof, that I can demonstrate, one simple thing, give them a choice, and I can prove based on their choice that I can do that. And then we repeat that enough times. And then if we do that like 1,000, 10,000 times, and always come out on the right side, this green guy is going to be pretty confident that I can actually walk through walls. So that's the cliche example that everyone uses for zero knowledge proofs. Let's go to a more exciting one, or more confusing, if you will. So this in computer science is a really hard problem to solve. This is a graph, and these are nodes and edges here. And apparently in computer science, like you've probably played that game in high school where you had the picture of the world and you had to color in each of the countries so that no country had a similar color. Well, it's the same thing here. Notice how in node 1, it's connected to 2 and it's connected to 3. And notice how they're different colors to 1. So in computer science, I don't remember all my graph theory, but apparently this is quite a hard problem to solve, NP complete or something like that. Yeah, so notice how 2 is attached to 1, 3, and 4, but you notice all the colors are different. So that's the tricky part. That's the puzzle of this task, and you have to color it so that they're all unique. So here's a perfect solution for that. Oh, I'm so clever. Look at me. Copied it from Google. Here's the solution. So the challenge is, if this is a competition to like $1 million prize to solve this puzzle, how can I show to you, my colleague, my friend, my competitor, how can I prove to you that I've solved this puzzle without actually revealing all these colors? It's a tricky problem. I'll give you a solution in a second, but let me just point this out here. Notice how the fact that this is red doesn't actually matter all that much. Doesn't matter at all. In fact, the only important thing about this being red is that 4 and 10 and 9 are also red at the same time. Does that make sense? It's not the color, but it's the fact that these two here are different colors, and that 1, 4, 10, and 9 are the same colors. And in fact, 2, 6, and 7 should be the same colors. So the color doesn't actually reveal anything. The only way we reveal information is if we reveal that 1, 4, 10, and 9 are the same color. So that gives us a bit of an insight into how we can solve this problem. So, and like, for example, this red could have been any other color. It could have been green, right? It wouldn't have changed the problem. It just would have had to make sure that this is green as well, this is green, and this is green as well. Would have been perfectly fine to change the colors. So one solution to this puzzle is you go to your hat room. You probably have a room in your house where you have 10,000 hats. So you just go to your hat room in your house and pick out, you just pick out 11 hats. And you come back to your zero knowledge proof. It's a fact that all zero knowledge proofs have to be done on the floor in front of you in a large map. So you just go to the floor in front of you and you place all of your hats. You place them on top of this is your floor, and you place a hat on every single node. In fact, let me just show you what a hat would look like. That's a hat there. Put another hat here. Thank goodness I have a use for all these hats, because I was really going to worry that I was going to have to throw them out. So you put a hat on each of them, and you say to this person, I think they're known as the prover, or the verifier. I'm the prover, I think. I'm not sure. And you say, all right, here's my graph, and they're all covered with hats here, as you can see. I will let you choose any 2 random hats. And what you'll do is you'll pick them up, and I want you to verify that the colors are different. And if they're different, then I've showed, at least for one part of the graph, that the condition of no 2 adjacent nodes having the same color is solved. So what you'll do is you go, okay, I'll randomly pick this one and this one. And you go, aha, look, they're both different colors. So it is true this time. So go, excellent, fantastic. And what we do is we do that again. Let me put those hats back on. Now, since I only have 2 hats here, I'm going to have to reuse the same image. But the important thing that I do differently this time, remember, like I said before, the color of each of these nodes doesn't matter. It's just the relationship of the colors to each other. So what I'll actually do, this is the revealed map here. I'll just color all the nodes a different color. So I might color all the red ones to yellow, 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 yellow. And I might color all the purple ones to red, 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 red. And all the blue ones I'll change to brown. Bloop, 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 bloop. And what I'll do this time around, he gets to do the process again, but I'll say I'll be using the colors brown, red, and yellow. Oh, that's not yellow. It is technically yellow, but whatever. And yellow. So what I'll do is I'll cover these all up in hats again. Hats. Here are my hats, you can see. And let's say he chooses to remove this hat and this hat, right? So, oh, no, I'll take that back. Let's say he chooses to pick this hat and this hat here. So he'll take them off and we can look at this graph over here. What he'll see is you'll see yellow and you'll see red. And he can verify that yes, yellow and red were the two colors we said one of the three colors we said we'd be using. And that these nodes do not have the same color. So he has not faked it yet. But notice how in the previous one, if I just go back, notice how this is a purple one. So he learned that this was purple, but notice now that this one used to be purple over here, but now it's red. So even the fact that he's actually seen the relationship, even though there is a relationship between 7 and this one over here, he doesn't actually know it because the color changed in between turns. So what we do is we continue this game. I'll just use my magic eraser. Reveal the hat, and the colors are different from each round. We do that again and again and again, and eventually he'll have done that enough times that he'll be pretty confident that I haven't faked it. And the reason is, if I faked it, I won't actually have been able to solve this puzzle. You know when you do like a Sudoku puzzle, and you're working or a crossword, you get all the way through, and you finally get to a one little corner, and you're like, damn it! Oh, I haven't figured it out. So let me pretend that I've done all of this part of the puzzle correctly, and then I get to a little section where I just can't figure it out. I've just had to fake it. So let me get this light green color. Let's say this is the section where I've just had to fake it. It doesn't solve the problem because these are the same color, and I've just failed. But I'm just hoping, if I cover these all with hats, let me just see if I can color with hats. I'm just hoping that he won't pick them. Color with hats, color with hats, color with a hat, color with a hat, 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 hat. Now each time I'd have to go and each time we do reveal some hats, I'd have to change the colors again, otherwise I would leak information. But let's just say, he might pick this one and this one. And he goes, oh no, they're different colors. All right, I believe you. And let's do another round. So he might go this one and this one. He goes, oh, different colors, I believe you. I would normally change, the purple would be a new color and the teal would be a different color, but I don't have a magical iPad. So he goes, okay, I believe you there. I'm really hoping that he stays away from these ones here. So let's have a look what happens when he goes to those ones. He'd go, all right, I pick this one and this one. Oh, I stuffed up actually. This one and this one. And I go, no, damn it! He's found me out. He's noticed that two of them, adjacent ones, are the same color. Therefore, I haven't actually solved the puzzle. I'm actually a huge phony. I fooled him for a little while, but eventually he found me out. And if he did this 1,000 times, if we did this 1,000 times, taking the hats off, or he took off every permutation, then he could be fairly convinced that I knew the puzzle. But because I don't know the puzzle and I had to fake a bit of it, eventually he found a case where I had faked it and it was revealed that I didn't know it. But you could imagine if we kept on doing that a million times, and every time I could find a perfect, I could demonstrate here, and the colors had changed since the last round, so you couldn't learn anything about it, then that would be pretty convincing proof. And I wouldn't have to reveal my beautiful solution. So that's one example. Let's think about another example. So everyone knows Sudoku puzzles. Sudoku puzzles, I love them. Oh, no. And the properties of a Sudoku, the way a Sudoku puzzle works is you have these columns, and you have these numbers in them. And you have to basically, a solved Sudoku puzzle has to have all the numbers from 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Has to have all the numbers in a row. In a column, that's a column. And all the columns here, they all have to have the numbers from 1 to 9. You can see because I gratuitously stole this from Google, this one's solved, which is great for me because I don't have to do anything. So it's got all the numbers from 1 to 9 in every column and all the numbers from 1 to 9 in every row, and every square here has all the numbers from 1 to 9. So that's how a Sudoku works if you didn't know that or forgot. How could you, my question is, how could you prove to another person that you had a solution for a Sudoku puzzle without revealing the actual answers to the Sudoku puzzle? It's an interesting question. Have a pause, have a think about it, because it is quite rewarding to figure out for yourself. I'll let you pause now. Okay, you didn't pause the video, but I admire your curiosity. So one solution would be, let me just draw a scaled down Sudoku puzzle here, because I don't have too many hands. Let's just say instead of having 9 by 9, I just have 3 by 3, right? You can see here, these are like a sort of Sudoku. And for this one to be solved, you need to have a number in each cupboard, right? In each box. So 1, 2. So see how I've solved this. This has the Sudoku property. Got all the numbers from 1 to 3 in each row and in each column. We don't really have squares in this example because we don't have 9, but assume that it has that property as well. Well, how can I prove that I've solved this miniature Sudoku? Well, one thing I could do is I could get rid of the numbers. I won't get rid of them yet, but every time I see the number 1, maybe I'll just color it red. So taking from the other example, and wherever I see 1, I'll just color it red. And then G, maybe I'll color, every time I see 2, I'll color it green. To do that, color it green there. And maybe every time I see 3, I'll just replace it with the color blue. Now what I could do is I could cover up this entire Sudoku puzzle. This is black, you're not meant to be able to see it. I could cover it all up so that you can't see it, which I trust you can't. And yeah, I'll do this side as well. Right, so covered up all my Sudoku. And I give you an option. I say, all right, what I'm going to do is I will reveal, can I use a white pen? I'll reveal one column, one of these columns, or one of the rows, or one of the little subsquares. I don't have any subsquares, but I would, if I did, I would offer those as well. You can pick any one and I'll reveal it. So maybe you say, oh, I pick this first column. So what I'd do is I'd go, all right, no worries, I will reveal that to you. Here you go. And there you go, you can see, and when I reveal that, you'll be able to verify, okay, he's got red, he's got green, he's got blue. And I'd tell you these colors up front, and you go, okay, right, all those colors are unique. I don't know what numbers they are, but they did represent numbers. So, okay, yeah, he solved that column. And then we repeat again. Now I'd go back into the Sudoku, and maybe every time I saw 1, instead of changing it with the color red, I'd change it with the color green. I'd basically shuffle the colors because I don't want to leak information. But what I would do is I'd cover them back up again and say, all right, I'll let you choose another one now. You can pick a column or row or a subsquare. So you might pick this one here. So, all right, I'll erase this one. And, oh, very tricky. I screwed up, I think. And it was this one. So I'll reveal this one here, and then you can see quite clearly that none of the colors are repeating there. So you can quite clearly verify that, okay, green, I don't know which number it corresponds to, but it did correspond to a number, and so did blue, and so did red, and they're all unique. And then we keep on repeating that again and again, and each time I do it, I'd go back and change, green might correspond to 3 next time, and I'd shuffle it each time, because I don't want to reveal information that this one here is the same number as this one. So that's why I have to shuffle the colors each time. I'd continue and continue and continue. But if I was a faker, let me just erase all of these. If I was a faker, and I think we've all done this in a Sudoku, right? We got into the corner and it's like, God damn it. Just ignore this little corner down here where I've stuffed up. Well, if I'd covered those, if I was a faker, let's say you asked to see this row. Oh golly, I erased too much. This row, I'd have fooled you, right? But if we do it more and more times, eventually you're going to come around and you're going to ask for this row, and I'll go, damn it, you've caught me out. So that's the property of zero knowledge proofs, that you repeat them again and again and again, and you can do them 10,000 times, a million times, and somebody that does know the solution will get it right every single time. A faker, a person like me, can get it right some of the times, but eventually with statistics will be caught out. So that is a zero knowledge proof, and that's that little test that you can do to verify that you don't leak any knowledge. There is actually another solution for the zero knowledge proof for a Sudoku puzzle where it doesn't rely on probability. We don't need to do it a repeated number of times. I can do one algorithm over this wonderful Sudoku puzzle here. Excuse me. And by the end of it, you'll know completely that I've solved it, and you won't know a single thing about a Sudoku, about where the numbers are placed on the board. And what it does, I'll give you a little pointer here if you want to pause and think about it. It involves laying down playing cards. So have a think about that and pause the video now to see if you can come up with a solution yourself. Okay, you didn't pause the video. I'm very disappointed in you. Anyway, let's go to that solution. So here it is. What it involves is you go to the solve Sudoku, like we saw up here. And every time you see the letter 2, what you do is you go to a deck of playing cards and you pull out 2 copies of the number 2. And you just place them, you pull out 3 copies of the number 2. And you place them face down on top of that number. Like I said, all zero knowledge proofs need to occur on the floor in front of you in a giant form, a giant printed Sudoku form. So likewise, so maybe this was the number 2 up here underneath it. So you just put 3 of the 2 playing cards on top. Maybe this was 4, so you put 3 of the 4 playing cards. This was maybe 7, so you put 3 of the 7 playing cards on top. Now what you do that for the entire board, right? So maybe there was a 7 here. So what you do is you put 3 7s there, and you put them face upside down. And what you do is you say to the person that wants to verify that you know this, you say what you do is just go along here and pick up the first card on top of the pile. Just pick them up. So they go through and pick them up, and you get them to, they can't see them yet. You just get them to shuffle the cards and then flip them over. Now if this Sudoku has been solved, all the numbers from 1 to 9 will be in this column, and therefore the top cards of all of these piles will be the numbers 1 to 9. So when they flip them over and they've been shuffled and they verify, they can just verify that all numbers 1 to 9 exist there. And you say to the person, all right, go down every column, just pull the first card off, shuffle them, and flip them over and check that all the numbers 1 to 9 are there. Do the same thing again for column 3, 4, 5, 6, 7, 8, 9. When you've done that, you verify that all of these columns solve the property or hold the property of the Sudoku puzzle. So the columns are solved. Now what you do, you still have 2 cards remaining on each of these numbers. You just go across the row and you pick up all the cards. And you get them to shuffle it and then flip them over. And then again, they can verify that 1 through 9 are there. And you do every row. And then when you've done that, there'll be 1 card remaining on top of these numbers. And then you just get the person, I'll do this in a different color, you just get them to pick all the numbers up in one of this top grid, and this grid, and this grid. And each time you pick up the cards in one grid, you shuffle them, flip them over, and check all the numbers 1 through 9 a day. You repeat that again and again and again. And then very soon you'll get to the end, you'll have no more cards remaining, and you've verified that each of the numbers in each row, column, and box are there from 1 to 9. So, without revealing anything about the Sudoku, you've been able to demonstrate to somebody that you have solved the Sudoku puzzle completely. So, it's quite a cool example. So, not all zero knowledge proofs need to have that statistical part of it. The key part of a zero knowledge proof is that no information about the solution or the thing that you know is revealed. So, this is quite an elegant solution. But if I move my head, just go to zero knowledge proof wiki. Doesn't need to have the probabilistic component of it. There's a few properties of a zero knowledge proof. I'll leave the proof of that as homework. No, just kidding. Definition. So if the statement is true, the honest verifier will be convinced of this fact by an honest prover. And I think it's this one here. If the statement is true, no cheating prover can convince the honest verifier that it is true, except with some small chance of probability. So that's that soundness property that we're talking about, that it should be convinced with like 99.999% accuracy, or in the case of here where you can complete it, you can prove it 100%. That's some cool examples of zero knowledge proofs. Very likely to be an exam question in my opinion. But have some fun thinking of solutions for zero knowledge proofs, and yeah, enjoy. Good luck.